Hello everybody, let's start today's tutorials. See the link for the Colab notebook. We will follow this link. I will be working on this notebook. Today I have quite ambitious plan. Let's see how much we can do. First, we will talk about Lasso and bias variance trade-off. We start with the Lasso reach bias variance trade-off, and then we will look at it from the theoretical perspective using simulated data, and then we will work with it, apply reach and Lasso to real-world data. Then hopefully we will finish it within the next hour or so, and then after that we will talk about fitting linear regressions, univariate models, ARIMA models. Okay, so let me start by sharing my screen. Okay. 1 second. First, I start by importing libraries that I want to use. Sorry, I want to connect to a local runtime. By the way, I noticed that many of you are using, not many of you, some of you are using Jupyter Notebook, which is great, but just for you to know, you can use Google Colab and connect it to a local runtime. I like working in Google Colab more because it has better code refactoring, code completion capabilities, and I just like the interface more of Google Colabs, but I just always connect it to a local runtime, so it is running not on the Google server, but on my local machine. And if you like Google Colab, you can do the same. Then it's basically like doing your Jupyter notebooks, but with Google Colab interface, if you like it. Let me make some this is just, oops, I haven't launched this. This is just settings for figures, not so important. I will be using. So I want to demonstrate the bias variance trade-off applied in the context of reach and Lasso regressions. This is what we talked about the very last lecture. So what I'm going to do, I'm going to use 45 regressors. Say I'm going to use the number of observations, 50, which is quite small relative to the number of regressors. So I would I'm going to assume that the true model, I'm going to be generating the true model where all 45 regressors are significant. I mean, they matter. I'm going to do say 1,000 simulations. Let me number. We can put it here. And I'm going to use let's see. Okay, that's fine. And then I'm going to consider the following model. So there will be P regressors and the error. So what I'm going to do first, I'm going to, let's see, do get the random number generator, whatever it is, some default random number generator that generates uniformly distributed values. And I'm going to draw key values for the beta coefficients. We can see them here. So I draw them and I leave them, whatever they are. But I don't want to have this big array, so I just redraw them. And so I do it once and I don't touch it. In the next code, I will let me first show how I would run reach on some simulated data. So suppose I want to simulate data. Standard normal. I want to draw train data from normal. Well, I can do it from uniform, doesn't matter. Suppose I draw it from normal. And values P regressors and observations P regressors. And then I will construct Y train. I will draw epsilons also. Train that would be random number generator, standard normal, and 1. So this is my error. And then I'm going to construct the outcome variable, which will be strain rule plus epsilon train. Then given this, so this code, we can run it. It will just generate random XY sample. What I want to do now, first I want to run a reach regression. I call it RR, doesn't matter. I'm going to fit intercept. And say it requires some nonlinear optimization. So I put the tolerance of nonlinear optimization relatively strict, 10 to the power like this, -12. So this, I'm going to use this reach function from the sklearn linear model package, which is the canonical Python implementation of reach. And I'm fitting an intercept here because neither, remember during the lectures, I told you that we need to scale X data regressors in order to avoid scaling confusion. And I'm not doing it. This is okay, because this is just a simple example. And anyway, I'm drawing them from standard normal with 0 mean and 1 variance. So I'm already drawing them from a normalized distribution. And I also fitting an intercept, which, remember, reach doesn't penalize intercept. And basically intercept captures anything if y is not non-normalized. So by default, I usually include it. Depending on the context, you might include or not include the intercept. Then reach has this penalty parameter. I could have specified it here. By default, this parameter is 1, is this alpha. This is the penalty parameter. In the lectures, we called it lambda. In the implementation of reach, it's called alpha. I want to set it separately here, just because later on I will be changing it. Then once I'm ready, I specify it reach. I can fit the regression with the data. And then I can say, look at the coefficients. For now. So let me go lower and try changing alpha. I will be not changing the data, but I will change alpha. So if I put alpha higher, then you see that coefficients are lower. Sorry, with alpha higher, coefficients tend to be lower. Higher alpha means higher penalty. And when alpha goes to a large number, then coefficients supposedly go to 0, but they never exactly reach 0 with reach. So now so this is how you fit reach. That's it. Then if you want to do the prediction, we will do it later with the data, with the real data. Right now, let us no, we will do it here. Sorry, we will need to do it here to see the bias variance trade-off. Yeah, let me now let me do the prediction just to show how it works. So suppose I fitted it with alpha equal to 1, then I can generate some test data. The same way, so I want to do the same thing here. In your test, say just suppose one value. So that would be my test data. And then I can do predict. And let's call it y test set. Let's see, like this, and let me just do this so that I get a number, and then I can calculate, say, y test set minus y test. Well, doesn't like this. So that would be a usual way of apply the trained model, like a reach, and then calculate the residual, like x test set. Now let me now combine everything and do two things. One thing, I'm going to do a very nice graph that I will be changing alpha. I will be varying it from small values to very large values, and I want to show you reach parameters, how they look. Just in the lectures, I showed a figure on the slides, but I want to show you how you can generate the same figure in Python, which is, I guess, maybe practically when you're working with the real data, not maybe terribly useful, but it's just nice to see how you can generate the kind of picture, how parameters change as we change alpha, the kind of picture that I showed during the lectures. So what I'm going to do now, I'm going to specify here even earlier. Let's call it lambdas because we call them lambdas in the lectures. Oh, we can call them lambdas or alpha. Well, let's call them lambdas. So what I'm going to do, I'm going to specify, get them on a linear space. But let me do it as power of 10. So they will go from 10 to the power of 3 to 10 to the power of minus 2, which is from 1000 to 1000ths. And say I take 20 of them. So, okay, that would be my lambdas. You can see how they look. So they go from 1000 to 10 to the power of minus 2 as powers of 10. So 1000, 500, 300, 162, and so on. Now, what I'm going to do, I will generate the data. I will not use here any test, so put it here lower. I will generate data only once. And then what I will be doing, I will be running reach many times. And fitting the model. Then I'm going to be saving coefficients. In this coefficients list. After I do this, let me, I think it will be quick. So what lambdas, yeah. Lambdas coefficients, and I'm going to present them. So x scale a log in x scale, and I'm going to, well, I can show how it looks. So as we go from lower values of lambda to higher values, you see coefficients go to 0, which is what we expect. So I just wanted to show this fun graph, how you can construct, and then we can add, so say x set, what is that, x set, x label lambda, and then let's see y label coefficients. Okay, something like this. Okay, so it's just to demonstrate how it looks with reach. And then let me, since we are on it, show how the same figure would look if we are doing Lasso. We basically will be, sorry, I want to use this like this. I want to keep name LL for Lasso. So RR will be my reach and LL will be my Lasso. So the same thing, but with Lasso. Oops, something didn't work. Let me see what's going on. So first here, set for us. What did I do wrong? Allow Lasso coefficients and the train. This, no, this one. Reach return small coefficient. So looks a bit funkier. Lasso looks funkier, And the most important thing is when lambda reaches 10 or even 9, all coefficients collapse to 0. Some coefficients collapse to 0 even earlier. So this is our lasso. Now, let me call this part let's see. Coefficients of region lasso. And now let me, are there any questions at this point?
If we know that one coefficient goes to 0 with lambda equal to, well, if some coefficients go to 0 earlier than others, does it mean something to us?
Does it mean what?
And does it mean something to us? So does it mean that they are not so important for the model?
So remember we discussed during lectures that it's you need to distinguish between importance in the sense of structural dependence or causal effect. So I mean, not causal, structural dependence, that some variable is structurally important, that changes in that variable change the outcome. That's one thing. Another thing is if this variable helps in achieving a better forecast. So we focused on this second question: if the variable helps in achieving in improving a forecast. The first question is a non-trivial question. If Lasso at some point gives that some variable has 0 coefficient, does it mean that this variable structurally is not important? So this is a very non-trivial question, and the answer to this question, at least to some extent, has been given only a few years ago by Viktor Chernozhukov at MIT, who proved with co-authors that the lasso has this oracle property. As you increase lambda, and if some of the coefficients go to 0, then it means that this variable is structurally not important. Now, we are not talking about we are not discussing neither the conditions when this should hold, nor we are interested in this question here. We are interested just getting as best forecast as we can. And for us, the fact that this coefficient goes to 0 potentially means that this variable it's not the right thing to say that it's not helpful in giving the forecast. Sorry, I should say that it's more perhaps the right thing to say that in sample this variable is not important in explaining the outcome. Like I would say it carefully, like would formulate it carefully like this.
Okay.
Okay.
Could we say that this variable is adding this variable adds to variance more than it contributes to explaining the bias?
No, we cannot. We don't know the bias variance trade-off here. Well, can we? Or maybe we can. Okay, let me be more careful here. Actually, I don't know. Maybe we can in some sense. This is a good question, and I don't know the answer. Maybe some statisticians worked on this. I haven't seen an answer to this question. But now we will be looking at the bias variance trade-off, and we will be seeing how potentially bias increases and variance decreases as we increase, bias increases, variance decreases potentially as we increase lambda, and that in a way means that some variables are contributing to variance and I have to be careful here because first of all there might be no linear dependence, or there might be no monotonic dependence here. So let me demonstrate what I want to demonstrate, and then we might come back to this discussion and I will show what I mean. So let me now I will work with range. What I'm going to do, I will be simulating lots of data. I say again, reach. So I will do it once. Then I will be let's say for sim index range, number of simulations. So I will be simulating data, then I will be running over lambdas for each simulated data set. Let me do this. Then set rows feed. Let me let's y test that's and to remember. So I will be then saving all my Sims number. Let me do one more thing here. Say 100. So I will be doing then 100 draws of the test variables. Well, maybe even let's say 1000 as well. Then okay, let me see. Okay, so I want to keep lambda's number as well. So what I'm going to do now, this number and simulations number, test sims number, and let me also draw okay. So here I draw test observations. Then I draw for each simulation, I draw train data. Then I go through lambda, I feed reach. Yeah, then so y plus that's let's see, test simulation number. Like this. Lambda index and simulation index. And predict x test. Okay, like this. Let's see if it works. Nope. Float object is not callable. Which one? NP nonce. Is it like this? No? Okay. Okay. And doesn't matter. Okay, that should work. From range, I see. Let's see. Reshape. Perhaps like this. Okay. Now it works. So I needed to drop additional dimension here. So now it will take a while to do this simulation. Nope. Let's see what's wrong again. Let's see what happens. What I say? This. Nope. Well, let's see if we do this. Nope.
Maybe you have to reshape X test.
I don't think so. I think this is okay. And anyway, I'm doing this many times in a loop. So let me see. One. Like this. Could not broadcast what's going on. Let me see. Array from shape. Squeeze, maybe squeeze. Nope. Hey, taking forever. What's going on? Okay. Looks like squeeze worked. Okay. So I needed to get rid of this additional dimension. So now it's going to take a while to finish it. And while it's doing this stuff, let me write, so we don't need this anymore. Now I'm going to be doing a bias variance trade-off decomposition for each lambda. So first, I will calculate for, so I have my y-test heads. Let's say means. Y minus heads. So I want to, this will be x is 0, x is 1, x is 2. So I want to average across the first axis, I mean the last axis, which would give me y-test hat means over simulations of x train. The next, I want to calculate squared bias, y squared bias, y squared. So what I'm going to do, I'm going to subtract from this. So that would be my expected value across simulations, but not across y's. So y is also of large size. Then that would be for each simulation of x's, what is y bias, and then I will need to average across this as well. So I will do it in a second. So I'm going to do take to the power of 2. And then now I'm going to calculate the mean, average over y. So I average over this dimension now. And this will give me squared bias across all for each lambda. So I can show you. Should be 20 values. Nope. What did I do wrong? Again, let me see. Okay. Let's see this. Does it work? 10, 20. Y, okay, and y test heads. Y test. Sorry, what I'm doing. Y test. Okay. Okay, nice. So I got 20 values. The bad thing is that they look the same. Why do they look the same? Something is wrong. Let me see. So what I'm doing here, I subtract across that's supposed to give me 20 A's. Sorry, was a mistake. Redo. Okay, while this is being performed, I will want to calculate variance. So I continue doing my bias variance decomposition. So I calculated here, this is supposed to calculate for each lambda the bias, the theoretical bias through simulations. Then y variance what I'm going to do is I'm going to take, so I need to y-test heads. I need to subtract no, sorry. Need to calculate variance over the second axis. So again, I calculate, so if we look here, I calculate variance across simulations, and then I calculate average variance across tests. So we can look print. Okay, now we get something sensible. And I'm going to plot in a second, but before I plot these things, let me just show you that I indeed did the bias variance decomposition. So remember the risk of our forecast should be equal to the bias, the squared bias, plus variance, plus irreducible error. So I want to show that indeed this is, I can do this decomposition works. Just to double check that I'm not making any mistake, because I know that these two terms plus the irreducible error should give me the mean squared error. So y MSE is equal to simply y-test heads minus y-test for each simulation index squared for index in range sim number, and then I should average it over everything. Because it's a two-dimensional array. Okay, so let me perhaps write it like this. Okay, so now potentially, so let's see what MSE is. Okay, so it's for each lambda, this is my mean squared error. So potentially, if I subtract bias and subtract variance, it should give me irreducible error, which is 0. Let me see. I wanted to get 1, but I didn't get 1. Why I didn't get 1? Y test, epsilon test. So I got 0. Let me see. I guess I average it out here somehow, but I'm not supposed to. I mean, it shouldn't average it out. Something is. Sorry. This was the bad part. Why? No. Y test heads. This is correct. Y test heads, variance. I see. This already includes irreducible error. Got it. I see. Okay. This one already includes it. Okay. So, but basically we get right. Okay. So we get all zeros here. So indeed our decomposition works. And irreducible error is in this Y var. We defined in the lectures, we defined this variance as variance over this minus this guy minus no, strange. Okay, let me move on. I will think about it. This supposed to include, this shouldn't be not 0. This shouldn't be 0. It should be like a constant, like 1. It should be 1 because the variance of my error is 1. I will think about it during the break. So let me move on. But at least I demonstrated that the decomposition works to some extent. Now let me show this decomposition of variance trade-off. Show the plot. So One, y squared. Okay. Oops, sorry. Here we go. Okay, so let's see what we observe here. So this solid line is the mean squared error. Basically, so on the on the horizontal axis, we have lambdas. When lambda is 0, we are in the OLS case. When lambda, and let me actually, while I'm explaining this, do the same thing for, launch the same thing for Lasso. Nope. Lasso gives me too many warnings. Doesn't converge. That can happen with Lasso because these are all numerical methods. Okay, while it's running, let me explain what's happening with reach here. So on the horizontal axis, we have lambdas. On the main line, the solid line, is our risk for each lambda. And when lambda is 0, then we are in the OLS case. When lambda is a huge number, then basically we predict y just by its mean. We basically bring to 0 all the regressors. And you see how mean squared error falls and achieves its minimum. So this is expected mean squared error, which is the risk. It's expected over the data sets and over outcomes. So it achieves some value for non-zero lambda. We can look why this happens. When we increase lambda, we see this dashed dotted line corresponding to variance falls and keeps falling. So the more we reduce lambda, the smaller is this line, the variance, and by squared keeps increasing. And the usual thing here, which is the usual thing for, well, not the usual, but often when Reach gives good performance, we have this, that for quite a while, for some range of lambdas, bias doesn't increase much, while variance falls a lot. That allows us to decrease the risk a lot. Now, back to the question that Daria asked, is it that when some of the coefficients of some of the regressors go to zero, does it mean that these regressors were contributing to variance too much? I guess the correspondence between these green and orange lines allows us to see how was the cumulative effect of these coefficients. Well, sorry. Now, as I'm explaining it, I just thought about the following. If you look in Reach, if you look here, there is no linearity in how coefficients go to zero. So like here, the value of this coefficient says negative. Like for example, here, it's close to zero, but then it increases, then it falls. So I think the answer to your question, if some coefficient goes to zero, can we say that this coefficient was not so important?
I mean, maybe, well, every coefficient goes to zero, but maybe if we compare some optimal lambda with the case when everything is included. Well, let me, I wrote it down. I'll put it in the chat. Maybe that would be easier.
Okay, so at optimal lambda, some variables are dropped, bias increased, variance decreased. We hope that this yields a better, because the variance is reduced to a greater. Yes, this is correct. Could the reverse be said, adding back these variables increases variance more than decreases bias? Were the ones that contributed to variance the most? Could it be the case? But adding these variables with what coefficients? It might be, but we need to formalize this. And why would you even, why would you ask this question? Why are you interested in this question?
Well, I mean, conceptually.
Right, but I think overall, there might be, I mean, we need to formalize this question, because what it means to add back this variable, with what coefficient? Do you like scale back lambda? I mean, decrease lambda.
Okay, I mean, like run OLS and then run Reach and compare which ones were dropped.
Yeah, you know, I don't think we can say this about individual variables, because like all the variables are shrinking, all the coefficients, sorry, are shrinking, and we cannot say overall as a group, for the group of those coefficients, perhaps this is true, but I'm not even sure about that, because at the same time, coefficients of the variables that remained, they also shrunk. So it might be tricky. There might be something like this, but you know, it might be tricky to talk about this. I think perhaps and look that with Lasso, there's also no there is no monotonicity in how coefficients go to zero. So some coefficients may go up, some coefficients may go down as we change lambda. So it's tricky to talk about this question. And everything changes. All coefficients change. Some increase, some decrease. Like for example, if you look at here, coefficient increased more to a value that is larger than it was at OLS estimate, at the OLS estimate. So it's not like OLS bounds everything. OLS estimates are the largest. As the group, they are the largest, I guess. For the in the sense of this, say in the Lasso, as their sum of the mean values of these coefficients, absolute values of these coefficients, is smaller on the Lasso than on the OLS, but individual coefficients can be larger. So that's why it makes it a bit tricky to answer your question. Maybe there is no sense in which we can talk about it.
Okay, I think I get it. Well, maybe in real cases, the regressors are even intercorrelated, so that's hard to say. Okay.
And okay, and this is the result for the Lasso. And I think all the warnings were coming from this part, probably. This is the part where all coefficients collapse to zero. After lambda equal to 9, basically all coefficients collapse to zero. And you see that with Lasso we reach it's kind of the meaning of the coefficient lambda is different, but anyway, the same holds here. Bias increases not so much initially, while variance falls, but perhaps we are not achieving that drastic reduction in mean squared error as with reach. We can compare. So here the minimum is approximately 5.2, and here what we have with reach is smaller. So here reach outperforms Lasso, but it doesn't have to be the case. One peculiar feature of this example was that all regressors were related to the outcome. In these cases, reach tends to be better than Lasso, while in the cases where some regressors are truly unrelated, Lasso tends to be better. You can experiment and say you can just put some of the coefficients here in beta true literally to zero and then rerun everything, and it can happen that most likely then Lasso will be better, will outperform reach for the optimal lambda. But basically I just wanted to demonstrate the point of this exercise was to reinforce what you learned about variance decomposition, how it looks, compare Lasso and reach. And so I want to deliver this point that it's not necessarily then one is better than the other in situations, even with the simulated data in the real world. So you need to be working with both.
How do you choose which one to use? exactly.
Yeah, one second. Let me finish, and then I'll talk about this. And then the third point that I want to deliver here is how you calculate a risk numerically. So we talked about risk a lot in theoretical terms. I just want to emphasize that this is kind of an approximate simulated expectation that we take when we calculate the risk. So we do expectation across the training data, or the data on which we train the model, and then on the test data. So we do these two integrals in the background, but we do them numerically, and in lectures we did them theoretically. I just want to make sure that you register this point, and you maybe go back and look at the codes, and you understand what's going on here. Now, further, right? You asked how do we choose between optimal lambda, or how do we choose between reach and lasso?
How do we choose between reach and lasso?
So, this is basically, there is a more broader question. How do you choose between different forecasts? And one way to think about it is, so this is model selection, basically. And one way to do it is what we were doing with forecast evaluation. You calculate, if we are talking about time series, this is what I did during tutorial 2. Well, you didn't attend. But basically, we need to do the divide data into train and test. So we have a data set. We defined it into train and test. Then we train our model on the train set, do the prediction on the test set, calculate the loss. Like very often, this is just root mean squared error. And then we can compare the loss across different models, and we perhaps choose the one that has the lower loss. But so this is the basic approach. Then things don't end here, actually. One issue here is that it can happen that many models will be giving similar results in terms of root mean squared error. In this case, we usually, in practice, the advice is to select the most parsimonious model, the simplest model. In that sense, if Lasso and Reach give roughly similar results, even if Reach is a little bit better, but if they give roughly similar results on the test data set, then probably the advice, not probably, the advice is to select, to go with Lasso, because Lasso tends to give more parsimonious models. It tends to zero coefficients faster.
So we build a model, then simulate data, and try to use both models and compare them. Is it correct?
We are given the data, right? And we divide the data into train and test subsamples. Then we estimate our set of models on the train set subsample, and then we evaluate their forecasts on the test.
Okay, so we need to try both models always.
Yes, we always try several models, and then we select the best. But again, the story doesn't end so then some models can give similar results, and the advice is to go with the most parsimonious model. But then usually you can do even better if you start combining models. For example, you can combine models with some weights. We don't have the time in this class to talk about this, but just keep in mind that, again, the story doesn't end here. The next step, once we constructed the best models, like we select the best lambda parameter for Lasso, select the best lambda parameter for reach, then we can actually combine this forecast for these models by some methods with some weights, for example, and the combination can be better than each model individually. And that's kind of, there is a little bit its own topic. It's its own topic, how to combine different models to achieve a better forecast. And we actually are going to talk about it a bit in the context of random forests and boosting trees, which the idea there is combination of hundreds of bad forecasts to get a forecast that is actually quite good. So let us take a break here. It goes slower than I expected, but okay, at least I explained this part. And I want to, once we come back, I want to continue with Lasso. Because I want you to use it in the next assignment that I'm going to give you. Okay, so let us reconvene. Yes?
Can I ask a related question, like over the break or in the end, probably?
Yeah, sure. You can ask now. So just for everyone, we will reconvene at what, like 5:10. Okay, yeah, ask the question. Oh,
Okay,
no, sorry, not 5:10, 11:10. It's 5:10 in Tokyo. Yeah,
well, can I show the screen?
Sure, yeah. 1 second. Huh?
Well, I drew a picture,
Mm-hmm.
and it's related to static and cross-validation forecasts. Like basically, if our goal is to forecast 3 years ahead, for example, I think if we consider only this 3 years ahead period, the resulting forecast for the static method can be better than the cross-validated one, because cross-validation yields the best average forecast for 3 years ahead, not the best one, like in terms of MSE K. I think that's correct, right?
I don't know. You know, you cannot compare this MSEs coming from the first and the second. And yeah, can we, by the way, I'm not sure about terminology. I think I called that this is, in the second tutorial, I said that this scheme that you call cross-validation, this is like a cross-validation counterpart time series, but
expanding window. Right.
Yeah, like expanding window forecast. I'm not sure we can call it cross-validation, but anyway, yeah.
Well, it's cross-validation using an expanding window forecast, not k-fold, right? But
right.
Okay. I'm saying that if we're interested in like only these 3 years ahead, the very last 3 years of our data.
Right. Of course, yes.
So
I am not sure because we are calculating the average, right?
well,
Or maybe we
like
add them up.
if the models are different, then here in the static case, there was the option to choose model 2 as the best, yet model 1 was chosen. So
I see. So okay, if model, does it mean MSC? Interesting question. Let's see. If model 2 is not equal to model 1, we chose different models based on this and that. Okay. Does it mean that this can... I don't think this is true. Because just logically, the model that performs better on average. Okay, maybe it is true. Because in the static sense, let me see. Perhaps, yes, perhaps you're right. Perhaps this is a curious question to ask, but right. Perhaps it's just if this is not correct, then we would have chosen model 2 in MSE in the first case. I think this is correct logically. Yes.
right. Well, then if choosing between model 1 and model 2, which one should we choose? I mean, this question is based on my results for the assignment. So, so well, I did the static one and the expanding window cross-validation, and well, I rejected the so-called model 2 in the static one. Actually, it was like quite middling, but expanding window gives it as the best model on average, like perhaps because earlier the MSE 1, 2, and etc. Were better than for model 1. So
yeah, I guess.
I mean, should I trust expanding window cross-validation?
Well, there is. I will tell you more. Even should you ask, or should you trust the static? Because
well, right.
I will tell you why. It's here is a third way of doing this. You can do a rolling window.
Yeah.
Where
I
you
could.
right, the size of the training sample, you keep it unchanged. So you keep shifting it as you shift through as you go through the data. And then the logic behind this is that the relationship between predictors and outcome is not necessarily time invariant, and so we could potentially be relying too much on the past history. So it's better to discard some of the past data. And so a rolling window forecast might be more precise. You know, then the question was this, which one should you go? So you do the static forecast and you go yeah, let me think. This is I think well, I know that people prefer the second method because like cross-validation, because it's it's more to the spirit of what we were trying to achieve, theoretically, minimization of risk. What we are doing here, we're kind of feeding our model. So we have a model in terms of the structure, and then we are feeding that model different data sets, this expanding data sets, and then we're calculating the performance in prediction in the next few quarters, periods, and then we are averaging across them, and that is like an empirical counterpart of our theoretical measure of risk. So in that sense, the second approach is more to the spirit. And then this is what people do. So perhaps going with the second approach is better, because think about it in the following way. You potentially want to be applying your model, your forecasting procedure many times, like each month the data arrives, new data arrives, you redo, and then you do your forecast. So perhaps you should be sticking with the model that consistently through time gives you the best result, now and in the future. And how you check which model gives you consistently the best result, you do the cross-validation. Does this make sense?
Yeah, I understand that it seems more robust. Well, I think if choosing the model, not, I don't know, the performance on the test set, on the very last test set, then it's, yeah, then I agree. It's just like a bit sad that there is a better forecast for 3 years ahead in the data that I have, based on the data that I have. And I'm saying like that model 2 is better. But maybe for some abstract data, and not abstract, but for some data that I don't have, that is really the future data, maybe that's better on average.
Yeah, right. And that's what we are trying to achieve. Like sometimes you would be worse, sometimes you would be better, but on average you will be winning, or like doing a good forecast.
Okay, then I'll do that.
Hmm.
Maybe I'll do the rolling window too, but I'm not sure.
Yeah, I didn't explain it, but it's very simple. You can do it. I think it's very simple. You just choose the window size and then you keep moving it.
Yeah, I'll try to. Thank you.
You're welcome.
A couple of questions about the assignment.
Mm-hmm.
First of all, what if in assignment 1 our chosen predictors turn out to not be very good at predicting GDP? Is that okay?
Yeah, it's okay, because anyway, I just want to see what you're doing and like you understand, because when you will be, there are several things here. First, this is not how people predict GDP. Like the way I showed it in the lectures, it's just, I mean, in lectures, in the tutorials, this is just to give you a sense of good, how you would approach this problem. Now, if you think about the problem that you have in the real world, you have in certain quarter, you have all the variables like GDP, some producers index, some consumer sentiments, and all this values, all these variables, but you don't have them for the next quarter. And so then you want to forecast GDP for the next quarter based on only the lagged variables. And so what we were doing in the tutorials and what I ask you to do, in practice you don't do it, but I just wanted to play around with it a bit. Then in practice you do first you start with a benchmark univariate model for GDP. You use it as a benchmark, like you estimate some ARIMA model, and then you quickly move to vector autoregressions, and perhaps you throw in lots of variables, and you use factor models, which I don't have time to go through, but it's not that difficult. And then you use some things like Lasso based on the previous variables, on the pre-locked variables. Now, if you have more time, suppose you're employed by some consulting company that wants to outperform the GDP forecast. This whole thing of selecting what impacts GDP forecast will take you most of the time. And in this class, we just don't have, you don't have the time in your home assignment to go through all possible things that could impact GDP and try to select the best ones. So I don't require, just whatever you found, just demonstrate how you can apply the tools that you learn. Because again, in the real, if you are doing the real forecasting, collecting the data, selecting the data is a huge task, because you can just see all these packages that are ready for you in Python. Once you have the data cleaned and ready and collected, it's just like pushing button after button and then seeing what performs best. But collecting the data, that's where you spend like 80% of the time.
Yeah, I see. Thank you. The second question is what are the formal requirements for code? So as I understand, the quality of code will be graded. So
yeah, I will look. Right. Thank you for asking this question. Yeah, I should have written this. I will look at the quality of your code, because I'm a human being. I'm not a machine, and I will be reading your code. So if just it's super badly written, then I don't understand anything, then how I can grade you. Then I will be using some subjective, like if I don't understand anything, then you will get like 5% of the grade. If the code is a bit dirty but it's clean, then perhaps you get like 90% of the grade. If the code is clean and everything is perfect, I mean, and everything is correct, all the comments make sense, you explained what you received, all the results, then you get 100% of the grade.
So the main thing is that the code should be readable.
Yes, yes. It's like when I was, when I started working as a professional programmer, that was the first thing that I went through, the training how to write a readable code. Because like when you're working in a large team, your code should be transferable. Other people should be able to look at it and understand what's happening. And then there is even a book about how to write good code. And I used the company that I work for, they used training from Google. So Google has, the company Google has their training for how to write a readable code, and my company used the same training. Yeah, and one of my friends at the time joked that like you're spending with your code more time than with your boyfriend or girlfriend. Your code should be as good as your boyfriend or your girlfriend.
Can you also maybe give a hint how different should be the results in the assignment about stocks when we compare?
Yeah, talk to Daria. You don't talk to Daria? Daria got the right result. So basically, in Bayesian, you should see falling portfolio with the falling portfolio share with the horizon.
The falling optimal weight.
Yeah, falling optimal weight. Give me now 1 second and we will continue with Lasso. All right, so now I want to go to the analysis of the real data. And probably it's going to be quite quick. Well, let's see. But there are certain issues when you're working with No, this is not what I wanted to do. I didn't want to do the copy. So when you work with the real data, things and you're trying to apply Lasso Reach, the code would look almost like what we did here, the same stuff. So it's using Python is quite convenient. You specify the model, set parameter lambda, alpha, whatever, fit, predict. And then you apply the rolling window, trending window, the forecasts, evaluate the model, and things like that. And the only thing is scaling. So people sometimes make mistakes with scaling, and that's the only thing that I want to emphasize. And I just want to show how this works with the real data. So let me I lost my notebook where I had it. So this one. Okay, got it. Okay, so let me share this one with you. Oh, I'm not sharing my screen. Sorry, I thought that I was. Okay, this one. Okay, so this is a new notebook. So first I will use the same data that I used in the examples with the European GDP. You've seen this part. So I loaded data on European GDP from 1997, quarterly data till 2020, and then a bunch of 5 indicators and 5 variables, regressors: consumer confidence indicator, industrial confidence indicator, industrial production index, and harmonized index of consumer prices. This is the stuff that we worked with before. So what I'm going to do now, I'm going to first add like variables here, and so I will immediately create, like, instead of just 4 regressors, I would create 9 regressors. So, and let me like Okay, so this is the original data, and then I put leg data, so one leg before. And then I will be running a regression of GDP on all the variables at the same time period, and then all the lagged variables. We haven't done it, and this is an obvious thing that we can do. And actually, in reality, when we are trying to forecast GDP, we don't have data, usually the same data. And for this quarter, we work with only lagged data. And we are trying to predict next period GDP. Now, so we can we can easily run a regression. This is the same as what we did without locked variables, but now we can run it with locked variables, GDP on all the consumer, confidence index, industrial, confidence index, producer index, and the inflation, and then all the lags, including GDP lag. And we can look, GDP lag is significant, industrial production index significant, consumer, well, barely significant, but industrial production index at this time, concurrent industrial production index is significant. Okay, so now what I want to do with this, I want to, and we can check all the autocorrelation of errors and heteroscedasticity, all this stuff. One thing that I didn't emphasize enough previously, there are many tests for testing serial correlation in the errors. And in the previous lecture, we talked about, tutorials, we talked about Darwin-Watson test, and which is routinely reported. And I always forget, Breusch-Gottfried, Breusch-Gottfried test, I think, which is based on Lagrange multipliers. And my recommendation from reading and thinking about it, and not only mine, but of smart people, is to use this good, oh my gosh, what's the name? 1 second. Breusch-Gottfried. Why I keep forgetting? Breusch-Gottfried LM test. There is, in many textbooks, you can find people using what's this test? There are so many tests, and I don't do them. I do one. Breusch-Gottfried, and even forget who is the author of this test. In many textbooks, you can see people suggesting using what's this test? Second. Lung box test for serial correlation. And I suggest that when you're testing for serial correlation, you just stick with the Breusch-Got-Freeland test. So we can, let me just put it here, because it has theoretical justification when we have a lag dependence. When we deal with the lag dependence, Darwin-Watson or this Lung box test, they don't have theoretical justification, even though some textbooks provide them as the tests for serial correlation in the autoregressive specifications. It's not correct. And this is, if you want to know where it's explained well, there is this excellent textbook by Fumio Hayashi, Econometrics. This is one of the, I think Bruce Hansen also, so there is an excellent textbook on econometrics, Bruce Hansen, that was published this year, but he's a super good econometrician in Wisconsin Madison. And he has been working on this textbook on econometrics for years, and now it's released, and you can download the PDF on his website, and that's the ultimate book that all of you should read. It's big and it has everything that you should know, but also there are some other textbooks that explain some parts better, like Fumio Hayashi. It explains better why you shouldn't use Lung box test. So I'm going to just drop here the serial correlation test. Breusch, good print. So don't use this one. Use this one. Say just one lag. This okay, so the zero hypothesis, no serial correlation, and the p-value is quite large, so we reject serial correlation, and we just go by this test. Okay, now I want to jump into reach estimation. First tests, let's say, yeah. I will use 8 quarters for the forecast, and I will do just a static forecast. So first I'm going to split the data into train and test. I like doing this. Okay, so first I split my data set for the with all the length variables. Then I'm going to separate. It will be convenient for me to separate this test and train into X and Y component. You can see, for example, test X. So just 8 last quarters. And say test Y, just GDP in the 8 last quarters. So then the next thing that I'm going to do, I'm going to scale the data. Remember, now pay attention, in the simulations before, we didn't scale the data because we were just drawing them from normal 0-1 distribution and there was no need, and anyway, it was a numerical exercise. But now when we are working with the real data, we must scale the data, which I explained during the lectures. When we apply Lasso reach, we must be scaling the data. And now here's a thing that often I see people make mistakes. If I earn $1 for each student, or for, and not only students, the codes that I saw who make these mistakes, every time that I noticed these mistakes, probably, well, I wouldn't have been a billionaire, but probably I would have had my favorite $5 coffee every day in Tokyo. So watch what we are going to do here, and I will tell you the mistake that usually people do, and I bet when I will be checking your assignments, there will be, maybe not, but there might be at least one group that will make this mistake. I say this, and still there are people who are making this mistake. Okay, so scale the data. We need to scale the data. For this, we are going to use standard scaler. You can check the standard scaler. It's a super convenient function in Python that scales the data, basically subtracts mean and divides by standard deviation. what I'm going to do, I'm going to apply this scalar fit transform to def train X. So what it does, it would create this new data set, and let me make a data frame out of it. And quickly wrap it. Data. So yeah, let me show first what it returns. So it returns this ugly array, a matrix, two-dimensional matrix. I want to make it nice. So I'm going to wrap it in a data frame. Frame X. Okay, so this is my scale data. What this scalar fit transform did, it applied, calculated the mean of each column, subtracted the mean, then calculated the variance, and divided each column by the variance. So if you say calculate MP mean, the frame scaled, you get zeros. And if you calculate variance, you get 1. If you do it for the original data, you obviously get not 1 and not zeros. Now, if you look at this scalar, this function fit transform did 2 things. First, it calculated mean and variance, and then it transformed the data. You can check. So this is def train mean of def train X. You can calculate. You can check of the scalar, and that's exactly these values. And the same for the variance. Exactly these values here and here. So the scalar, just a convenient way of doing. You can do it manually, of course, the scaling, but the scalar is convenient, and the convenience comes in here. Now you can do the test X scales. Of course, you need to scale the test data. And now this is the point where people make a mistake. What people would do, they would scale the data like this. And then they would work. So they will scale the test data independently from the train data. This is wrong. And then you will work with 2 scale data sets. So you will train your model on the scale train set and apply it to the test scale test. First of all, if you have just 1 observation, you obviously will get 0 here with this function, because subtracting mean from 1 observation would be just 0, and variance will be infinity. So that would obviously give something wrong to you. I don't know what it's going to give when you have 1 observation, but people don't notice this because they usually have more than 1 observations in the test data set. That's why they usually don't notice that they're doing something wrong. Then why another when you're applying your independent scaling on the test data set, you kind of how should I explain it? You're using a less, what is the point of this transform here is making everything on the same scale, but then this mean and variance that you use here, they potentially they approximate mean and variance in the population. And when you're using mean and variance calculated of the test data, then you're also approximating mean and variance in the population, but you're using fewer observations to do it. And so you're getting a less precise estimation of mean and variance. Then what you should do instead, you should just do this, which would apply mean and variance calculated on the trained data set to the test data set. Is this point clear? Anyone?
What have you changed?
Okay, what I've changed. So it was like this, and I did like this. So what it did, it applied mean and variance calculated on the trained data set to the test data set. Understood? Not understood? Anybody is with me? I see what somebody wrote. Okay, understood, I guess. Now,
So, like we scale them, taking into account the parameters of scaling of sample, right? Well,
of the train sample.
What if we normalize the whole that
Perfect. I wanted that question. Yes. Perfect. Thank you very much, Fedor. What if we do this? You like on the whole data set, right? Why we don't do this? Because it leads to so like suppose we do this somewhere or even earlier, like here is our the lag. Why don't we do like something like this? Well, okay, so suppose we first do this. Let's say they have x, they have x data is equal to okay, so why don't we do this, and then they have x is equal to the scale transform, they have x, and then we just scale, and then we just work with the scaled. Why we don't do this? $1 million question. No, I mean, and many people do this mistake. So, okay, somebody wrote something. That's what exactly I was saying. No, we shouldn't do SK transform on test. Sorry, not fit. Sorry, transform. My bad. Yeah, that's what I meant. Sorry. Why we don't do? Thank you. For why we don't do this on the whole data set? Anyone wants to guess?
Because this will contaminate the training set with the test
tests,
data.
the training set, exactly, with the test data. We will have data spillovers. Daria, where did you learn this? Did you guess it, or you saw it before?
Well, I did a machine learning course once last
Okay,
year.
perfect that you that's what's left. I mean that you remember this. Basically, we don't do this because we contaminate the train set with the test set, and they should be no information about test set should leak into the train set. They should be totally separate. And then, by the way, when we do all kinds of data transformations, like when we work, say, with GDP and we want to detrend it and remove seasonality, we should do all of that on the training set and then apply it to the test set. All right, so we don't do it because there will be a contamination. And that's why we do this. Okay.
I
Yes?
have one question about related to test sample and the training sample. So we use that split to choose a model, but shouldn't we, in the end, when we have chosen a model, use the whole information available to construct our final prediction?
Perfect. Yes, indeed. That's what we usually do. We first do this train split stuff where we use the test data set to do all the model selection. We can actually even do several, like a hierarchy of train sets, train splits, if we have enough data. So use like some parameters to do train, test 1, test 2, and so on. And then you can go into hierarchy, whatever. But once you're done, you basically take your whole data set and train the final model on that whole data set, and then use it to forecast. That's what we do, yes. Okay. So I scaled this. Now we understand this. We understand two issues. One, you cannot scale the full original data because there will be data contamination, and then you apply transformation of the trained data to the test. Perfect. And then I want to do just to wrap it into a nice data frame. Right. Okay. No. What did I do wrong? Oops. Okay. Done. Now we can also check just as a key inverse transform minus no. What I'm doing wrong? Def train expand. Okay. Yeah. We need to do the same stuff here. No. Okay. Heat transform, transform. What's going on? What's going on? No, this works. These forms and things. Hmm. Ah, sorry. Here's okay. Oof. Okay, nice. So I just showed that I can transform back the data, and that's how we do. We can transform it back, and then we get the original data. Okay, this was just a reality check. Let me write it. Okay, and finally, we do say reach. We do the same stuff that we did before. For first reach GDP. Test next spelled, and let's see. Okay, so we get our forecast. Let me convert it into a nice data frame. Okay, and we can then calculate the mean squared error. Well, um, means now we can again wrap it into do this fun thing that I like doing. Say 3 minus 2, 20. Um, let's see what we get. Okay, so this is our lambda. Let me do a plot set. Let me do this. Okay, nice. So what we see here is that we definitely get a bunch of improvement for lambda equal not to 0, but to something like here, less than 10, more than between 1 and 10, maybe, I don't know. What is this, 9? We can check. And this is MP mean index. How do you get the index? Work mean. 4. Okay, so this is how we do, and of course, as further, and we can look at the coefficients. Say, let's see. Print. Coefficients, 1. And you can compare them with print this is more or less I guess works -1. Let me just double check. Oh, yeah, when down this tiny. So interesting that we don't really get the coefficients that all of them fall, but it's just fun to examine. Of course, with the real data, you don't do such things, but still, it's fun. Let me just do the last picture because it's so much fun to do it. Like, let me do a figure like this. Interesting. So basically, this is our best lambda here. You see, not all coefficients collapsed. Like this coefficient increased actually. So this is the reach part, and then we can do. So that was our reach estimation. Then we can do the same stuff with Lasso. Lasso estimation, totally the same. So let's say not like this. Linkage methods. Then prepare data. Then this reach. So let me move this up. This up. No. I take a smaller value for the Lasso because for reach I took 3, for Lasso I take 2. Maybe even 1 is enough because it tends to, as you saw, it tends to collapse coefficients quick to 0. But okay, let's see if it's 2. So we go again. Mhm. Let me do this. Aha. Collapsed a bunch of them to 0. And let us do this. So we can actually go. So lambda here, probably even 1, we can finish here at like this. Go, let's see. Okay, yeah. So this is somewhere here is our result. Let us, just for the fun of it, to check the coefficients for the optimal. Interesting, very nice. And then let us compare. So the best optimal. So with Lasso we get 0.35. With Reach we get with Reach we get 0.57. So Lasso gives a better performance. Partially this is because Lasso doesn't, Reach doesn't put the coefficients exactly to 0. So we go with Reach here. Oh, sorry, we go with Lasso. Let me just, yes?
Why do we go with Lasso here? Based on what?
Because the optimal, based on the test data, on this example, which might not be the best, and I will talk about it in a second, but based on this example, our optimal test root mean square is this, which is smaller, which is bigger for Reach than for Lasso. So for Lasso, it's 0.35. We can actually plot them together. and then lambdas. I was redefining variables here and there, so let me restart everything, restart and run all, and I will explain in a second. Okay, our lambdas done. Done. Nope. Lambdas. Okay. Looks a bit funky, but basically this is the values what Lasso achieves, mean squared error, and what Ridge achieves. And we see that Lasso definitely is better than Ridge. So Lasso is minimum here in terms of root mean square error on this in this example, while Ridge is better here. But of course, so Nikolai, is this clear now?
Yes, it is. Thank you.
Okay, great. Now, of course, what we really want to do, this is just test was done without any like rolling forecast or expanding window forecast. So really what we want to do with this, we want to now do a rolling forecast with this, like now expanding window forecast. So we do kind of cross-validation, not just comparison on one data set, I mean on one test data set, but keep repeating this on several test data sets. This is what we discussed with Daria during the break. So that I leave it to you. I'm pretty sure you can now use this logic to do this rolling or expanding window forecast or the cross-validation. Okay, is this clear?
Yes, it is.
Okay, so I guess it went way longer than I wanted, and it's like 10 minutes left till the end. I guess this is pretty much it for the Lasso Ridge. Of course, the payoff will be bigger once you start having more data. And like more regressors, and then Lasso might be giving you good performance. And yeah, this is how you apply it to the real data. The next thing that I want to talk about is the univariate models, but we don't have the time. We will do it during the next tutorial, which will be not this coming Tuesday, but next Tuesday. But I'll see, maybe, so I need to talk a bit about VARs and trees. I will start this next lecture with trees, try to cover them as much as I can. And then if time allows, I will talk about VARs. If time doesn't allow, then we don't cover VARs. I think we don't have the time for VARs. Okay, probably we will just finish with univariate model. Yeah, that would be the plan. Okay, that's it for today, and let me know if you have any questions.
There will be another assignment, right?
Yes, there will be another assignment. Basically, I will ask you to apply univariate model, trees, because trees are so important, and Lasso reach to your data.
So when will it be approximately?
Yeah, I can basically we finish our lectures and seminars December. Which one? December. What did I write on Discord? Um,
In our timetable, it's the 20th of December.
right, right. Okay. So there will be no tutorials next Saturday. I'm out. I will be at a conference whole weekend. Then there will be last tutorials will be December 20th. So it's a bit tricky. So if I give you an assignment on December on the same day, and then I will ask you to submit end of Sunday. That would be like December 25th. And then the exam day will be December 27th. Yeah, I think basically I can tell you right now, I mean, I can write you right now. Basically, there will be no surprise. You need to, whatever you did for the assignment 1 with the real data for the Russian GDP, you would need to do the same stuff along the lines of what I did during today's tutorial. That's 1. Then I will talk about trees. That's 2. And then I will talk about univariate model fitting. That's 3. You can start doing Lasso now. Just do it to prepare. Your assignment, I will give it formally on December 20th. Well, I can give it even earlier. I can formulate it now. Okay, I can formulate it now. It will be due to December 25th. Okay?
Yes, if you give us the tasks like a little bit before the 20th, it will be
Yeah,
nice.
I will.
Because
I will write. Yeah.
okay.
But basically, you know what to do. The next task is to apply to your data set whatever I did today and explain what you see and select the best model. That would be the next task. I will write it. And then we'll do the same with trees.
Okay,
I
we
want
just have an exam week starting from 21st, and usually we close all deadlines before that.
Before the 21st, I see.
Yes.
Oh, what to do? What to do? 21st is...
Well, I don't know if it's allowed in the HSC, but I think 25th would be better because we would have a couple days after the exams to finish the assignment. Well,
Right.
that's what I think.
Yes, and also, I think last year, when I was teaching this class with Yulia Shapovalova, she was the lecturer. She did this assignment as a take-home exam. And this is allowed. This was allowed. So let us do it this way.
I just wanted to check if I understood the task correctly in part 2.2 of the current assignment about Bayesian approach. So the algorithm is as follows. We draw sigmas, for example, 100 sigmas, sigma squared. Then we draw for each sigma squared mu. So we have, for example, 100 pairs of mu and sigma squared. Then we generate stock returns for a given horizon. We take each pair.
But by the way, you have not 100 pairs of sigma and mu's. You have for each sigma you draw like 100 mu's also, because you have like a joint distribution of mu and sigma.
By the way, does it matter where we add iterations? Like we can do 100 sigmas and for each 100 mu's, or alternatively we could generate 10,000 sigmas and 1 mu for each.
Yeah, that's a good question. Actually, it's not an easy question. You know, it's all about numerical integration. Let me think. What would be, so right, you generate 10,000 sigmas, but then for each sigma you do 1 mu. I think interesting.
I think it doesn't really matter because we choose a point on a 2D plane anyway.
Right.
Well, but we integrate separately over sigmas and over mu's.
Yes.
So we need many mu's, I think.
I think we need many mu's. I think what you're suggesting would be like the second option would be less, the approximation error would be large. So it's better to draw, definitely it's safer, it's a safe option to draw 100 sigmas and 100 mu's instead of 10,000 sigmas and 1 mu.
Well, we lose on precision for each sigma, but we gain more sigmas. So we cover the range of possible sigmas more densely. I'm not sure.
It depends. It depends on the shape of the distribution given sigma. The shape of the distribution for mu's. If it's very like compact, then we will get 1 sigma will be enough. If it's widespread, and especially if it depends on sigma, then we will be, for like tail sigmas, we will be getting lots of errors, even though we have. So I think still we need to just logically thinking through it. For each sigma, we should draw many mu's.
Okay. But then we generate stock returns given 10,000 combinations of mu and sigma. And I also think then it does not matter if we separate those generated stock returns given a horizon, because we then no, from the point of view of an agent, each stock return that we have generated is equally likely. So we can just bunch them together. Then we calculate 10,000 wealths to calculate the expected utility.
As opposed to what?
Well, we could have calculated 100 wealths 100 times, but and we would have 100 expected utilities. But I think that is not.
Yes. What you mean? You mean then when we make a draw of y's, the returns.
Yes.
For each combination of mu and sigma, should we make a draw of y's only once or like 100 times? Right?
No. I draw 100 times for each pair. I am talking about that then we can bunch them all together in one big list of possible y's.
Okay.
And use that list to generate however many wealths, and then calculate expected utility with all those wealths.
What is this bunching? What do you mean by bunching? You mean you say, let's say not 100 y's, but 2 y's. So for fix, suppose we have one pair of mu and sigma, we draw just 2 y's. I mean, for the like fixed horizon, we draw, like horizon is just one quarter. We draw 2 y's. Then for each of these realized returns, you calculate optimal portfolio.
I can show my screen.
Okay. 1 second.